Hello everyone, welcome to another lecture for drug delivery engineering and principles. So what we learned in the last class, we mostly talked about polymer drug conjugates, right. So these are polymers that can be conjugated to the drugs either in this format where a long polymer bone gets conjugated to small polymer to small drugs, or you can have a large drug like proteins and you can conjugate polymers onto them. What is the advantage of this? That one of the advantage is of course that it increases the size for these small drugs. So, their residence time increases as we discussed in terms of elimination. The kidney cannot clear anything below above 6 to 10 nanometers. So, it will have enhanced circulation as well as it also prevents any degradation by external proteases and all of that. So, these are some of the advantages here. Then we also talked about chemistry that we can use for different conjugations. EDC coupling is one to conjugate carboxyls to amine. We had thiol and maleimide click chemistry, which is very widely used to conjugate SH group to a maleimide group, and then we talked about several others as well. Then one of the polymer drug conjugate we talked about is pegylation, very widely used in the literature. These could be a single chain of PEG or could be a branch chain of PEG. Branch chain we found out is more effective just because it has a lot more area that it can cover as a windshield wiper. And then we gave a clinical example, something that is being used in clinic for IFN alpha 2A, where we showed that if you conjugate it with a branched PEG, it circulates much longer into the blood compared to just the free drug alone. So, today we are going to talk about some of the challenges with pegylation, and one of the major challenges that has come is the anti-PEG antibodies. These are antibodies that are generated against the PEG. So, about 4 or 5 years ago this was reported. Before then it was considered that PEG is a fairly inert molecule and it does not really induce any kind of immune response in the system. But in the last 5 to 6 years more and more people are reporting that there are antibodies against this PEG polymer that is being generated and induced in patients. Of course, one of the major purpose of the antibodies is to cause rapid clearance of anything foreign. So, these antibodies bind to their targets, and once the antibody is bonded to the target, the immune system clears those things up. They take this up through FC receptors and various kinds of other mechanisms. And so, what will happen is whatever drug you were conjugating with the PEG will now, instead of remaining longer, it will actually get removed much faster. This will result in low clinical efficacy and will also result in risk of severe reaction, because these antibodies then once they bind to their receptors, they generate quite a lot of immune response, lots of cytokines are being secreted by the immune cells. And so, all of this will cause severe reaction, and this will manifest in form of high temperature, fever, pain and all those effects. So, again not very desirable. What is even more concerning is that the anti-PEG antibodies have been found in people that are naive to PEG, and when I say that is basically that means that these people have never been treated with any of these polymer drug conjugate with PEG. And even then they have antibodies. Why do they have these antibodies? Is because PEG is also very widely used in several consumer products like eye drops and creams, and even though we may never have been given any IFN alpha treatment with the conjugated PEG, we are still exposed to the PEG on the basis of these drops and creams, and our body has been exposed to the PEG which has generated these antibodies. So, even the first time we will give these PEG drug conjugates, we will see that they are getting cleared very rapidly. So, here is just one example here. So, you see in case of long circulating, so you have different kinds of drugs that are conjugated to PEG. In this case this is a uricase which has an activity of over 21 days in subjects without the PEG antibody, with or without the PEG antibodies. But what happens is when the subjects are given the pegylated product, you get quite a lot of uricase activity which lasts quite a long if they do not have these antibodies, but when they do have these antibodies, these gets cleared very rapidly. So, as you can see, let us compare the 12 milligram example. In this 12 milligram blue curve, you see that the antibodies are the PEG products are being circulating for more than 22 days. However, once you have given once these patients have been exposed and they have generated the antibodies, when you give them again you see that they get rapidly cleared within 10 days itself. So, these are some of the issues that has started to come up with the PEG conjugation. So, then what are the alternatives? So, we do have other polymers as well, we have polyoxylenes, PVP, polybetadines and other kinds of polymers that are also being explored. So far none of these antibodies have been reported against these polymers, but having said that they have not been used as much as the PEG was. So, more and more research will tell us whether these will last or whether the body will also start generating antibodies against these particular polymers. One example here is norborine, which has started to come as a good alternative. So, if you look at the norborine graphs, you will see that it covers the protein fairly completely. The protein here is in blue and then the red is essentially your this polymer coating. So, it can act as a good alternative, but again as I said will only time will tell whether once this is started to use more and more widely, whether our body also generates antibody against norborine. One other alternative is very similar polymer to PEG, it is called poly-OEGMA, and what it is essentially an this functional group which is very similar to PEG. If you look at this unit, this is PEG itself, but in this case what is happening is small units of this is growing. So, the polymerization is on this end. So, previously if you were seeing PEG, that was being written as this. In this case if you see, this is only 9 units or you can vary these units around, but the polymerization is actually happening on this backbone. So, instead of having a long polymer like this with all of PEG, what you have is a long polymer like this with small PEG units hanging on it. So, this is something that has been proposed. And more research is now going into it, and at least the initial data is suggesting that this could be an alternative to PEG. And so, one of the paper here described the use of growing this polymer onto a single polymer chain of protein. So, what they used is they used the fact that the N terminal amine will have a different pKa than rest of the amine present in the protein core. And so, they use this pH differential to form a biodegradable bond at that site. So, in this case they used different kinds of chemistry at different pH to utilize only the N terminal, and then they grew this long poly-OEGMA chain with it. Remember, these small pendants are the PEG chain, and then the basic unit here, this is not PEG, but this is what is getting polymerized. And then they went ahead to show that the activity of this does not really change with the growing polymer chain. In fact, it is almost the same as the native protein itself, and like the pegylation, it also has quite a long residence time. So, the free drug gets cleared very rapidly, but once you conjugate it with this polymer, it stays for much longer. So, further to this, then they started evaluating whether such strategies can be used to prevent any antibody generation. So, what they, here is another paper by Chilcote group. We are going to talk a little bit about this paper. So, what they have used a protein called exendin-4, which is a small peptide which is used in case of diabetes to secrete insulin. And what they have done is that they have made a recombinant protein of this. They to this protein, what they have done is they have added a His tag, and this His tag is essentially used to purify this protein in downstream processes, and they have also added a small peptide sequence to it. So, what they can do then is they can do in their chemistry onto the small peptide sequence by using some enzymes which are fairly very specific. So, in this case they have now conjugated an initiator onto this C terminal of this protein where this His tag was attached. So, now instead of the His tag you have this whole protein containing the initiator, and once there is an initiator you can do your OEGMA reaction to essentially get a long chain as described previously. So, very similar strategy to what it was there, but then in this paper then they went ahead and showed that first of all the half life has increased. So, if you have only protein, you only have a half life of less than an hour, whereas as you increase these polymer chains molecular weight, you get a quite a lot of half life. And then finally then they showed that if they compare it to some PEG products in the market with the patient samples, what they find is these two products, the Crestexa and Adagen, are PEG based products which are already being used in the market, and if you expose them to patients containing antibodies against PEG, you see quite a lot of antibody binding to these products, whereas if they use their polymer, they do not see any effect on the antibody binding. And this is again showed in terms of another assay here, where their EG3 exendin-C-POEGMA does not really show any decrease. Okay. So, that was on polymer drug conjugates. As we go along, we are going to talk more about controlled drug release, and there are several systems for this. One is a diffusion control system, which is basically a reservoir system, where you create a reservoir and then release the drug on the basis of diffusion, or this could be a matrix as well, which is non-erodible. You can have a solvent control system, so these could be osmotic pumps, or there is some sort of swelling happening because of the presence of the solvent, and that causes the drug to come out. Or these could be chemically controlled. One example of this we already learned in terms of polymer drug conjugates. These could be bioerodible as well. So, as the chemical bonds in the membrane degrades, you will see that more and more drug is coming out. So, we will talk about the diffusion control systems first, and before we actually do that, we need to learn some of the laws of diffusion. So, the first thing we are going to talk about is Fick's law of diffusion, and what it is just a kind of an estimate of how the molecules diffuse. It is a model based on the random walk. And so, what typically happens, let us say if I have a sample containing a high concentration of your drug on one side and low concentration on the other side, these molecules are constantly moving and colliding with each other. So, the collisions will be more in this area than in this area. So, as there are more collisions, they will tend to move because of these random collisions towards the low collision area. And so, that is essentially what is defined as diffusion in this case through this model. And the diffusive flux, which is essentially the rate of the movement of the solute into the rest of the media, is then defined as J, which is nothing but is equal to the diffusion coefficient as well as multiplied with the change in concentration. So, this is how it is mathematically expressed. D is again the diffusion coefficient, which is going to be constant for a certain solute in a certain solvent. So, for a random walk, another term that is defined is a root mean square displacement, which basically means that if a molecule is just freely diffusing from one place, how long will it take for it to reach a certain distance, or how much time it would take for it to reach a certain distance. So, this XMS, which is the root mean square displacement, is defined as root 2 dt. So, that is again here d is a diffusion coefficient and t is just the time. So, if I ask you that if a particle takes time t to diffuse a distance L millimeter, how long will it take to diffuse 2L millimeter? So, you can use the above defined equation to answer that. So, earlier I am saying that L is equal to root 2 dt, in this case the t is capital, then what will be 2L, how much time will it take for 2L. So, the time taken will be what? So, let us say 2L, the time taken is x, is equal to 2 dx, then I can just essentially divide these two equations. So, I will get 2L by L is equal to root 2 d x by root 2 dt, ln cancel, these two also cancel. So, essentially if I square both sides, I will get 4 t is equal to x. So, it will essentially take 4 times as much, because it is a root relationship. Okay. So, then we define the second law of Fick's diffusion, and that is nothing but mass conservation. So, what it says is, let us say if we take a small volume, then it is a general mass balance equation, which basically means that whatever of that particular solute is coming in any of the directions. So, it could be in the z direction, it could be in the x direction, or it could be in the y direction. Then if you subtract whatever is going out, so let us say, and this is the going out in the x, this is the going out in the y, and this is the going out in the z, plus if there is any generation within that volume. So, let us say if a reaction is taking place also in that small volume, then that term will also get added up as generation. That should all be equal to what is the total accumulation in this particular region. So, if I then express it mathematically, you essentially get a equation which is this, which is nothing but this is essentially saying in minus out, the rate of change of C in each of the directions with the generation term, and this will then tell you how much over time the concentration is changing at that particular volume. And if I decrease that volume to very small, then it essentially will tell you at what is the concentration at that point. So, again this is also written as the d del square C is equal to dC by dt, if I assume that there is no generation, which is going to be the case in our case, where we will design devices and put them in the body and see how they are diffusing through in the body. So, let us take a simple case in this case. So, instead of having an x, y, and z, we will just say it is a one dimension system, and so only diffusion that can happen is in one direction. So, in that case this equation simplifies to this, where the only x term is remaining, the y and the z are gone. And then if you apply some boundary conditions, and so what are the boundary conditions here? So, what are we doing here? So, we have given amount of drug, let us say C0 at this particular time at x0, at a particular time at x0, at time d equal to 0, let us say. So, what are boundary conditions? Our boundary conditions will essentially be that at x equal to infinity and x equal to minus infinity, which is very far away from here, there will be no concentration of this particular molecule at that large distances at any time, whether the time is 0 or 1 hour or whatever. And if I define through these equations, what I will get is, if I solve this, I will get a function which is mathematically expressed as this. And if you start plotting it over time or over a distance from the source at different time points, you will get something like this. At a certain time, you will get a very high concentration at the source, and as you move away from the source, it decreases. At a time which is greater than the previous time, this concentration will decrease, because you already have quite a lot of it diffused out into the surrounding medium, and the surrounding medium will start to increase, and essentially it is going to follow a similar trend. So, next will be something like this, and it will continue to go like this till it becomes equal everywhere. So, another difference to that is a different state to that is something when we say the diffusion is from a constant source. So, in this case we were saying that the source is not constant, what you have put is essentially going to diffuse out in the media, and the concentration at that point is going to decrease. But now we are saying that the source is constant, that means that whatever you put at that particular time is not going to change at all. So, if that is the case, then what will happen is the concentration at this point will always remain C0, which is the concentration that you have administered, and as time increases you have more and more solute starting to diffuse into the medium, but still the concentration at this point will always be C0. So, if you go ahead and put these boundary conditions, so now in this case what you are saying is essentially for any time the concentration is always going to be C0 at x equal to 0 for any time greater than 0, and of course at t equal to 0 you had this to be 0 at any point away from the source. So, basically essentially saying that if this was represented again, if this is x equal to 0 at time t equal to 0, there is no concentration here or here. So, this is what is represented here. So, if you solve this, it essentially gives you an analytical result as this equation, and if you plot it mathematically like we did in the first case, you will essentially get at source the concentration will always remain the same, and as time increases this is going to give more and more into the surrounding medium, and with increase in time the concentration in the surrounding medium will also increase at all time at all different locations. Okay, so this was all for diffusion under aqueous conditions. What happens in cases where, let us say, the solvent is not aqueous, but let us say the solvent is viscous. So then, as I described earlier, the diffusion constant is essentially constant for a particular solute in a particular solvent. Now, if we are going to change the solvent, then the diffusion constant will also change. So, but the general form of the diffusion equation will remain the same. It is just that the diffusion coefficient is going to start to change. So, what if the diffusion, how will the diffusion coefficient or diffusion constant is going to change as the solution becomes more and more viscous? Yeah, so basically as you might have guessed already, since it is becoming more and more viscous, it will be harder for it to diffuse, the diffusion coefficient is actually going to decrease. So, the same things applies for several other factors, and if I define this using a Stokes-Einstein equation, which is used for defining diffusion coefficient of a solute, it essentially boils down to this, where Kb is the Boltzmann constant, T is the temperature in Kelvin, and mu is the viscosity of the medium, and then finally A is the hydrodynamic radius of the solute molecule. So, this equation is only valid if you are saying that the diffusing particle is large compared to the surrounding solvent molecules. For all drug delivery applications, we are essentially talking about the surrounding molecules to be water, which is fairly small, and most of our drugs are going to be much larger than water. So, we can use this particular Stokes-Einstein equation in cases where the viscosity of the water is changing due to some solvents. So, in case, as I said, in cases of protein, we can assume that since the solute radius is much greater than the solvent, this still holds true, and it can, then we can further show that this diffusion coefficient is related to the molecular weight with the negative of cube root 1 by cube root, and this in particular this is how it is defined for proteins. This equation changes a little bit for DNA. Again, you can assume most of the time that if the DNA is small enough that to be spherical, but we know that the DNA is a linear polymer. So, for DNA which is not a globular protein, they typically do not behave as spheres. People have done some empirical correlations to find out what is the relation between the dA and the molecular weight, and what they found is it is related with the certain power over the molecular weight. So, again this is mostly for information, this was empirically derived, but I just wanted you guys to have it in case you are trying to model the rate of diffusion of DNA, which is now starting to be used more and more in terms of microRNA and all those kinds of drugs. So, you have this term there. Okay, we are going to a little bit discuss on the size scale as well, since now I am saying that the protein molecule is extremely large compared to solute molecule or the solvent molecule, which is water. Let us talk about the size ranges of what we are talking about for proteins here especially. So, I mean this is a classic size scale, you have different sorts of objects to basically give you an idea. So, here we are saying that viruses are 10 to 150 nanometer, DNA can be anywhere between 2 to 10 nanometer, atoms are 0.1 nanometer. So, all of this is just kind of listed here. Hairs are essentially in microns, close to about 100 microns. So, this kinds of help us define what we are talking about in terms of size. So, let us do some protein size estimates. So, if we assume that proteins have no substantial pockets, so essentially they are very closely packed, and almost no water molecule is present in the protein interior, which we can assume for the most part. Even if there is water molecule, there is very few compared to the size of the protein. So, hence the proteins have fairly rigid structures with a Young modulus similar to that of almost plexiglass, and they have a density of about 1.37 gram per centimeter cube. So, now if I have to find a relation between radius of the protein and its molecular weight, assuming it is a spherical shape, then what will I do? So, let us continue with this particular equation and try to solve this. So, if I say that what is the relation between the radius and the molecular weight, to find that I have to first find out what is the relation between the volume and the molecular weight, right. And so, we know that volume is equal to mass by density. Now, since we know that, we can say that okay. So, how do we define mass here? So, let us say we are talking about 1 mole of protein. So, in terms of 1 mole of protein, we are saying the volume of 1 mole of protein is equal to essentially molecular weight. So, let us say molecular weight, and the density we just found out is 1.37. So, this molecular weight is in Daltons, 1.37 gram per centimeter cube. Now, since we have this, let us further define what is this volume in 1 mole. So, we can say that this is also equal to number of particles or number of atoms or number of molecules in a mole, so which is 6.023 into 10 to the power 23 multiplied by volume of 1 protein. So, volume of 1 protein molecule. Okay. And now that we have defined that, we can further expand this volume. So, this volume is going to be depending on how we are defining the radius. So, if we are saying nanometer, then it is going to be nanometer cube, and so this then further becomes equal to 6.023 into 10 to the power 23 multiplied by the volume of each particle is 4 by 3 pi r cube, where r is the radius in nanometer, right. So, now you have a relation between r and the molecular weight, everything else is constant. So, you can solve that, and if you go ahead and solve that, what you will find is this is already done, and what you will find is the relation comes out to be somewhere around r is equal to 0.066 to the times of the molecular weight cube root, where the molecular weight is in Dalton and r is in nanometer. And if you do this calculation for various things, what you will find is a protein with a molecular weight of 5 kilodalton is about 1.1 nanometer, and even if you increase the molecular weight by almost 100 times to 500, the radius only increases a little bit to 5.21, and that is because the relation is on the cube root. Okay. So, let us do another calculation. Let us do a relation between the average distance between the molecules and its concentration. So, if I say that a protein is at a concentration of a certain x molar, then what is the distance between the 2 protein molecules in that solution. So, how will you go about this? I will give you a moment to think before I start proceeding with the answer. So, in this case what we will do is we will make an assumption. So, let us say we make an assumption that for any particular concentration, the protein is completely tightly packed and there is no space. So, in that case, let us say we are saying that the protein is fairly tightly packed, and in essentially what we are now trying to find is the distance between the centers of these tightly packed spheres. Right. So, let us say if this is r and this is r, then our distance between average distance for a certain concentration is 2r, right. So, now if we have this assumption, how we can go about this? So, we can, what we can do is we can essentially assume that in a 1 molar solution there are 6 into 10 to the power 23 molecules. That means that there are 0.6 molecules per nanometer cube, right, because we know that this many are per liter, and if you do the conversion it will come out to be volume is essentially 1.66 nanometer cube per molecule, and then you can essentially do the similar calculation as we did before, and what you will find is the concentration, if we are saying the concentration is 1 molar, then the average distance between molecules is only 1.18 in nanometers. So, then that begs the question is, can you make 1 molar concentration of a protein which is let us say 500 kilodaltons. So, from the last slide we know that the size of a protein molecule which is 500 kDa is approximately 5 nanometer. So, something like that cannot be physically packed in a solution. So, that is why you have solubility limits along with other factors as well, and so that helps you kind of defining how much distances are we talking about. So, in proteins we are talking about typically nanomolars or micromolars, and so that gives you an idea of how far different protein molecules are, and that helps you in terms of diffusion kinetics and all. So, we will stop here. We will continue in the future classes to talk about more on the diffusion control systems as well as other control release systems. Thank you.